Dominic Bunnett from the Universität. And I thought about the finite automorphisms group of hypersurfaces.
Yeah, thanks for the invitation. I'm happy to be here. Deal with the kind of layout of the audience. I'm going to talk about groups. Everyone's going to go, yay! And then I'm going to talk about automorphism groups and varieties, and everyone's going to go, oh. But I'm going to talk a lot about groups and reductive groups, and in particular finite groups, group scheme. And yeah, I'll start out with algebra, because the question I want to talk about today is really, it's very, you can explain it to an undergraduate. It's not a difficult one to pose, but it's a difficult one to answer. So I start with the polynomial ring over any field. Okay. And I give it a grading by a finitely generated abelian group. And the one technical condition for today is just that each of these graded pieces is finite dimensional. Okay. And basically, the example that I want, there are kind of three examples I want to keep in mind. The one to kind of like, rest easy is you just take the standard grading by total degree. Okay, so we get homogeneous polynomials, degree D, right? The next one is, again, rank 1, right? But I allow my weights to be anything, right? So here, the variable weights, xi, are 1, okay? The next example is I say, okay, same as above, but I allow my variables to have arbitrary weights, positive. Okay. And then the last one is any degree. Not n, let's go with r. So n, r copies of z, and the degree of zi is just 1. What I want here is, like, in the case, let's just take the case of concrete example, let's just take Z2, and I want bi-homogeneous polynomial. X. So, for example, here, right, you can take x1 squared, so degree 2, 1, y1 plus x1, x2, y2. Okay, and I'll explain to the geometrists what this means. Okay, it's the problem of yesterday. Okay. All right, and so this is our setup. And the question we want to ask, right, is about stabilizer groups of homogeneous elements. So pick F inside some degree, right, some homogeneous polynomial. And we take G to be the automorphism group of S, okay, which preserves the gradient. Fixes the gradient. And this is sat inside the Cremona group, right? I remove the graded insistence, right? So just K algebra automorphisms, and in general, when you know the structure of these graded automorphism groups, it's not very difficult to prove. We know that G has the form of just the product of a bunch of general linear groups, semi-direct product with some unipotent parts. So these are non-reductive groups in general. One place where unavoidably non-reductive groups come up when doing geometry, algebraic geometry. Okay, so we have these kind of groups, and then the question, what's the question?
Where does it add into this? Yeah.
Into this one? Doesn't yet.
This picks an F.
Yeah, we picked an F, and I've written down my group, and then I let my group, so then G act on S alpha, and I want to know under what conditions is the stabilizer group of F on two? That's the question, right?
So that group is thematic, meaning that.
This here, yeah, this is a non-trivial result, which is like Cox and also then later by Bruns and Kuberlands. Yeah. So I mean, it's important in the context of the algebraic geometry. Writing that, like proving the fact that it's a gradient, that's not hard. Most people to write it down. Okay, so this is our question, right? And then give you an example in the standard case, right? If I take stabilizer with GL3 of say x cubed plus y cubed plus z cubed, right? You can write it down as isomorphic to, I can commute the coordinates, right? S3, but I can also don't at me about the direction of this semi-direct product. I'm not sure if it's right, but this. So we get this also if I have a cube root of 3 in my field, right? If okay, such that this is okay. And this is finite. Very good. Sorry, let me see. Right. And we'll come on, right? So classically, we'll write this up properly later. This was kind of, these questions, I mean, they're so easy to pose, they've been studied and thought about for a long, long time. People like Jordan and Lee were thinking about these things a long time ago. And if F is smooth, right? By which I mean satisfies Jacobi criteria, that is no simultaneous vanishing of partial derivatives. Okay. If F is smooth, then the stabilizer group this is GLN, sorry, F in this is now really the very specific case. Standard grading. Right. GLN plus 1 of F is cognate. Okay, so long as the degree is at least 3 and the N is at least 2. Okay.
So do you need any characteristics?
So no, nothing. And this, yeah, nothing. So, like, and to be completely honest, classically, if I write classically, right, I mean, this was proven for the complex numbers, or at least there was a proof. Okay, Lee knew how to prove it more or less over the complex numbers, but didn't quite, you need regular sequences and didn't quite know what they were. So there's a proof written down by Lee and by Jordan, and it wasn't fully fleshed out over the complex numbers, right? And then the kind of the straggling characteristics, so you always had to, then in the 60s, I'll write something later, Matsumoto and Monsky proved it for any field, so long as the degree doesn't divide the characteristic, but then Katz and Sarnak tidied this up in the 90s. This is going to be, yeah, thank you. It's good to get this out early because that's essentially what this talk is about, is this tidying up of characteristics and... Yeah.
One, everything being important in the book of the grading.
Yeah, it's homogeneous.
That means homogeneous.
Yeah.
And then the second thing is, if I was to look at the, I guess, or you variety.
I'm about to write this down. Yeah, I'm about to write exactly down what the geometry is that's going on. Right, yeah, a quick reality check for geometrists. It says that, okay, so grading the polynomial ring, okay, by gamma is the same data as giving a action of the corresponding diagonalizable group in here. Okay, but in the interest, just nervous. I don't want to be sloppy, so I'll just take this for this kind of setup, but it works in general, right? And this is the grading of this guy here is the same as this diagonalizable group acting on the affine state, the spec of the coordinate ring. Okay. And then what we're going to define y to be the GIT quotient of this action is diagonalizable, it's productive, we don't really have to worry about anything. This is d gamma. This is given this assumption, this finiteness assumption, okay? None of this is obvious, right? I don't claim this to be obvious. I'm telling like this is a story, okay? And I can point you in the right directions for it rigorously, just to give you some context, right? This is a projective toric orbifold, right? So this just means a toric variety without worst quotient singularity. And under this, so in this world, right, then X is going to be the vanishing locus of F. Okay, so if we take an F homogeneous, it's a polynomial in the polynomial ring, so its vanishing locus defines a locus up here, but it's homogeneous, so it's invariant under this group action, so it descends to a height. Okay, so basically, again, I mean, take a homogeneous polynomial. In this case, you think projective. It's a hypersurface in projective space. Okay, that's non-controversial. I'm just saying the story for toric varieties generalizes exactly and very quickly. Okay, this is right here, and this is the heights. Okay. Moreover, most of the time, okay, we have stabilizers. So this is kind of, I'll try. Just to be honest, this stuff is all a bit vague, and it's like they're quite subtle questions. Most of the time, stabilizer of your polynomial in F in the way that we've talked about here surjects with a finite kernel onto the automorphism group of the height. Okay, the concrete way of getting a hand, and you know this the kernel is very easy to figure out. It's trivial. So like if you can compute this, then you compute it. Right. And there's the last 2 or 3 years, there's been a lot of activity somehow. Like people in this kind of classical case, people have been computing these automorphism groups, okay, for various fixed degrees and dimensions. I've had a bit of a revival, I think.
Wait. Oh, most of the time, but not all.
Not all of us. For example, again, in the standard weighting case, the assumption is n and d is not equal to 2 or 3 or 3 or 4. Okay, and these are elliptic curves, plane cubics, right? And these are K3's quartic K3 surface. Okay.
So the automorphism going to be algebraic?
It's always an algebraic group, yes. Well, it's always a group scheme.
But affine you cannot.
I mean, in this case, it's certainly not affine. Right, we've got my elliptic curve itself sat inside. By the way, this is so yeah. In this case, for example, okay, there's a lot of distinction going on. Right, so in this case, like you say, right, so it's not a linear algebraic group because I've got this whole projective abelian variety itself sat inside it, and this is just an injection inside it. This turns out to still be finite. Okay? But this doesn't give everything. However, then in surfaces, this is something completely different. This is very delicate stuff. These are very useful things that people are interested in. We're able to study these quartic K3s deeply and they're complicated. But again, this is actually zero-dimensional. Okay, so it's a discrete group scheme, but it's not finite in general, which is another kind of. Basically, everything's nice except for when you have elliptic curves and K3 surfaces, and that's something which we talked about now. Right. Okay. So next. Okay. Again, for like algebraic geometers, like to do this, like for example, in this positive, like when the degrees we have some degrees greater than 1. This stuff starts to get messy because the toric variety stops being smooth and it's really truly an orbifold. It has singularity, right? But so often, what's going on under the hood, and what I won't really talk about today, is that we're going to be working with like curly Y. Is actually we won't take the moduli, but like the toric variety, but we'll take the toric stack. So that's which has as a not just a good moduli space, really a coarse moduli space. Again, this is top. If you're interested, has Y as its coarse moduli. Okay. And these are smooth delete methods. Okay. And that's kind of, yeah, unfortunately, this is like I'd say one of the main contributions, right? Is taking this old stuff, which has been done, but not applied to these singular cases because, you know, we don't know how to deal with what will turn out to be calculus on these singular cases. But you can use this kind of like, it's about 20 years old, this modernish stuff. Work on the stack, it's smooth, and you're kind of okay. But there are new results which exist on the level of varieties as well. Okay. Good. So the motivation before we kind of move on to some neat, right? Luckily, Lena gave us lots of motivation before, right? And like, if you're interested in moduli of variety.
Wait, can you make a specific question? I'm struggling with this D gamma.
It's D gamma, yeah.
And I was thinking this must be finite. But
No. It's a torus. It's a quality torus. It's a diagonalizable group.
so
Yeah.
for instance, if you pick the degree, this is the star.
This is C star, yeah. It's some kind of jewel, and the Greek theorist might be probably doesn't know. It's a jewel. Cartier jewel. It's a Cartier jewel.
And you take a second example that you list it there, then you get weight.
You get C star, but it's acting with the weight. It's actually you get weight projective space, and if you pick this one, you get two copies of C star, and you get products of projective space. That's the yeah. So I mean that will. I'll write this up here. So moduli varieties, like often components of moduli spaces. Are moduli of just hypersets. I'll give them my hypersets. And e.g., there are bits of K of this big K moduli stack, which can be interrogated by moduli of hypersets. So, and what's the data of a hypersurface? It's some degree given by alpha and some ambient space given by alpha. Okay. And basically, proving finiteness of automorphism groups is going to tell you whether these stacks are Lima. Okay, and then the next one is, okay, if we're interested in the case stability of these hypersurfaces, you want to use this method which Lena was talking about last time, which is better the more automorphisms you have. So in a way, this kind of screws you over, right? So, helpful-ish for probing case stability. And last but not least, right? So again, for the case stability, there are these kind of long results, starting with Matsushima, Chen, Donaldson. No, Sun. Sorry. Sun and lots of other people, Shu, Alpha, Dan Halper-Leisner, a bunch of people basically say, well, if my variety is K polystable, my finite variety is K polystable, then the automorphism group is reductive. Okay. Moreover, if it's K stable, not just polystable, then also is finite. Right? So the kind of wider reason that I'm looking into these things at the moment, I'm searching because it's an open question: are smooth hypersurfaces and Pn K stable or not? Right? We don't know. But can we find, does there exist a hypersurface in some toric variety with a non-reductive unipotent? Non-reductive unipotent ores. Okay.
Sorry,
Yeah.
I just asked what you mean stable.
No, you may not. Like it's a nice property. And it basically, like, it's these notions of stability we have in algebraic geometry which grant you admission to a moduli space. So if I'm trying to parameterize all varieties, right, I'm trying to fit them into some big, like, continuous moduli space, but they can perform they can deform in very degenerate ways. And I need to remove some of them if I hope to have a moduli space, which is, again, algebraic in some sense, okay? So these stability conditions, they come in lots of different forms, and David's case stabilities turns out to be a very good one, because with it you can prove algebraicity of the moduli stack, okay, and properness of a moduli space, whatever that means. They're nice. Yeah, exactly. They're bouncers to the club of moduli.
Some sort of English case.
Sorry, no. So this, I mean, okay, for this one, Matsushima proved it for smooth, and as did Donaldson, Chen, and Sun. But then it was recent, like 2 or 3 years ago, right? These guys proved it for singular balance. So now we know, and that means that which you absolutely need for the moduli stack to be algebraic, right? And have all these nice properties because they use this good moduli space theory, and you need reductive multiple group for this stack. So yeah, that's recent, and it's very hard. Okay. Great. Right, so let's talk about this classical case. We'll talk about how people prove it and how we can basically steal those proofs, use modern techniques, and generalize them. So, right. So there's a theorem, kind of pasted together. This is exactly the thing I was talking about earlier. So we didn't really have a proof, but probably knew how to prove. Jordan did have a proof over C. Then Matsumura Monsky did it in the 60s, more properly. And then characteristic assumptions were removed by Kaplan and Sarnak in the 90s. And this says, okay, so in this classical case, so S, we take the standard grading. Right? And we assume that N is 2, and D is 3. Then, if X is smooth, again, this Jacobi criteria, or smooth as defines a smooth variety, then this stab is finite. To the automorphism group, we'll let X be. Finite. And so we rule out cubic curves and we rule out. So, how does one prove such a result? So we won't give all details, but just a bit of a sketch. But there's this kind of this well-known thing. So we know that automorphism groups of algebra varieties are, or of schemes are group schemes in general. Okay? But they have geometric structure, so we can kind of study them and we can look. And if you look at, I mean, you know how to prove that, right? So every automorphism you can associate its graph to it, right? This embeds you in the Hilbert scheme of the product, okay, the automorphism group. That's basic because the graph determines your automorphism, right? So this gives you like a well-defined map into the Hilbert scheme. Probably the graph of the morphism. Yeah, so you take your automorphism X to X, right? You take its graph, right? And this defines a closed subscheme of X cross X. Yeah. So then, like this, you get an embedding of all of Port X into the Hilbert scheme of X cross X, and you can show this locally closed, like this. kind of clear this geometric construction. It proves that vortex is it's like, it's a sub-schema of the Hilbert scheme. So that's already kind of quite amazing that these things have algebraic structure. But then if you understand the Hilbert scheme well enough, you know what the tangent space to point to the Hilbert scheme. And it's just given by normal bundles. So these are things you can kind of, and once you run that down to the bottom, basically you get this thing which.
And why does that fail for
No, that never fails. What fails is the relationship between this stabilizer group and this automorphism. This automorphism group is always a scheme.
Okay.
So this is completely general. We have the Lie algebra, the automorphism group of X, right, is isomorphic to H naught of XT, right? My tangent bundle. So these are global over the complex numbers. When this is smooth, right, these are global vectors. Okay. And kind of more heuristically, you can understand this if you work over complex numbers. Like if I have some continuous family, so my automorphism group isn't finite, right? So I have some continuous family of automorphisms. I can differentiate this family at the identity, right, to get my element of the Lie algebra. But then differentiating this family, seeing where it moves, defines a vector field for me on my variety. This is kind of very old classical construction. Differentiate families of automorphisms gives me this. So thus, if I have no global vector fields, right, then my Lie algebra vortex is 0. Okay, so the group scheme is 0 dimensional. Discrete. Okay, if I was being very careful, then you would say a 0-dimensional group scheme. Right. So now we have a new aim, right? So the first thing that one has to do is that, so if we want to get this first statement, we have to relate stab and ought, right? And the first thing to do is to exactly construct this. To construct a map, so the first step is to construct stab G F ought X. Okay. And I won't talk about this. This is kind of a different thing. But you can do it, right? And then the second thing is to show that H naught of Tx is 0. Okay. So there's one way of doing it, but the oldest way of doing it was done by Kodaira and Spencer in the 50s. Okay. And essentially what they do is they're working with complex, they see these things as complex analytic spaces, right? They're smooth complex manifolds, these hypersurfaces, and they notice, right? They do calculus, serious calculus. And the main thing to kind of notice, right, is to translate going from the tangent, so going from vector fields, right? You remember your analysis 2 or 3 classes, right? Going from vector fields to differential forms, right? And the tangent bundle or tangent space or global vector fields is actually isomorphic to n minus 2 on x twisted by canonical bundle. Okay. It's going on under the hood. Right. So you translate this into these spaces here, and you look at vanishing. This so-called Bott vanishing, which is just, so I take my P forms, right, on Pn, okay, P forms on Pn, and I twist them by some. Again, those who aren't familiar, who aren't kind of dealing with these things all the time, basically don't worry. The point is, it's some calculus which was done, messing around with P forms and things like that, right? So, and block vanishing gives a lot of these equal to 0, except in a very few specific cases, and we will write down some short effect sequences later to show how this works. But basically, they study these things, they look at homology of key forms, and they prove this. Okay? The other way that Matsumura-Monsky went, okay, is noticing that, okay, well, F as a form is smooth if and only if its partial derivatives, which are themselves homogeneous polynomials, right, form a regular sequence. Right? And basically,
because mostly for I mean all from there is only zero solution for all this. And I think for regular sequences, what is very closely to toric. And if you take F1 and say for a sequence of homogeneous polynomials,
yeah.
If the zero set of that is only zero solution, then you can only in regular sequence. I think that's over and really close.
No, so it's true in general, but the thing that you need to check zeros over every finite extent, every algebraic extension. So like if I can take a sequence of polynomials in a polynomial ring over any field, and this I mean the way that you prove this is exactly as you said, like you look at the vanishing locus, but I mean I don't mean like the vanishing locus over a non-closed field. This gives me some subscheme I don't really understand, so I take it over. I just need to check it over the algebraic closure, basically. So yeah, the way you prove this is you prove that the common vanishings only over closed fields, but the remaining statement in the polynomial ring is true. This is it's like it's physical, it's an exercise in Bourbaki. Like it's kind of buried and discovered by Orlick and Solomon, I think, they gave this very nice quick proof. So how does this? Yeah, I mean, I don't want to go into too much detail, but this regular sequence business basically allows you to, like, using the Euler sequence, which just says that there, En goes to copies of another. Basically, now now we're really this would. I don't want to get too much into this because this is really the toolbox of a graduate algebraic course. Have a bunch of short exact sequences which you kind of know and you've seen, and you take long exact sequences and you just mess around with them and force them vanish. The point is, like, this is somehow the crucial point, and I write this up here because this is exactly what fails in our generalized case. Okay, but these generalized gradings, right? You do not have this equivalence. This smoothness condition is not equivalent to this regular sequence. So the method which kind of exists and was out there does not work. Okay. So what you need to do is you need to go back to this guy here and see and try and generalize this. And that's actually what also very important, I should say, is that this regular sequence method, okay, it works over every field, except, right, this method requires that the characteristic does not divide the degree. And this is a genuine limitation of the method. So then until the 90s, where yeah, okay, I'll tell you this. They're nice stories, right? But like Katzenstein say that Gabor pointed out to them that actually this Kadara-Spencer method works over any characteristic they just didn't really know yet. But they sat down, they worked out. And yeah, you can kind of tidy up, you can finish off this last characteristic that was open until the 90s. Right. Right. So this is like ridiculous that I wrote proof. Like the proof ideas. Nowhere doesn't come close to being a proof. Right. Okay. So today, right? I'm kind of gonna explain. I'll show you some of this stuff, some of this block vanishing stuff, what's going on under the hood. But basically, using this approach, right? You can prove the following. So this is due to myself and Caroline Amania. Right. This is, I think the proofs are done. It should be on the archive soonish. And it says, the first one says that, okay, if AI is invertible in K, or A naught after AN, and right, we're in this case where S is weight projective space case. Okay, so our variables have degrees A naught to AN. Okay, this is a shame. There's absolutely nothing you can do about it. Okay? In particular, you don't have to make out any real exceptions for the degree, right? Which is the nice thing, right? So for this case, right, and f is some homogeneous polynomial, which is quasi-smooth, right? I haven't defined this, and I won't, but again, it's the same deal. So it's just a polynomial, you check its Jacobi equation. Okay. X is quasi-smooth, and the degree is at least twice the maximal AI, okay, where you're allowed equality only if AN is strictly bigger than all the others. Okay. Then ought with standard exceptions, depth for K3s and elliptic curves. So I should say this is basically a theorem of S. Well, so what we did is so ESSA does it over C. Okay. I mean, I did it in 2021, but with more conditions on the degree. I needed it to be Cartier, so I needed all the areas to divide this. But basically, I mean, the serious thing, like these bounds, for example, important bit, these bounds are. Yeah, but you do it for arbitrary too. But we do it for arbitrary fields. So this here, this is the concept of us.
Do you prove that it's discrete? So
in the K3, yes. In this case, yes. This. In this case, not.
sorry, I mean the Romeo.
This is less than infinity. What am I talking about? This, yeah, this is finite. Right.
So your AIs are both weights.
Is it equal as well, or?
I haven't proven that, but over there'll be more restrictions. I mean, that's a very good question.
Yeah, I mean, I'll just.
It's a little bit delicate. In this case, it's tau.
Yeah. So worrying on the same way to start.
We have gone the same way to start with, which maybe actually no, we have. So it does follow. Yeah, I haven't stressed that. But yeah, it will be a tau over the vector long that these things are things that matter. Yeah.
I don't understand your hypothesis.
Okay.
Your AIs are weights.
My AI is a weight, and I have to assume that they're invertible in my field. So there is this. This is just some. This just says so that the characteristic AIs can't divide the characteristic of K. It's just a restriction on the field.
AIs are natural.
Exactly. So they have to be invertible in my field.
Your field is going to be. Yes. So if AI if the characteristic is true and AI is true,
Then we're fine.
okay, so you're kind of like projecting the integer into your field, and then you're calling that you're just.
This if you want it cleaner,
Okay.
if you want it cleaner, I
No, it's fine.
Yeah.
It didn't make sense when get it.
okay.
You know, with that addition, then
Okay.
you did that.
Good. Okay, so yeah, this order is finite. Yeah. Okay. Right. So this is kind of a generalization of this kind of work for myself before and the better.
It's finite. I don't say what it.
No, I can't say what it is. That's a wholly different problem. I mean, what we're doing is we're computing the tangent space. We can't say what it is. Okay, the next theorem. Yeah. So the theorem, which is again myself and Caroline, there's okay, so if y is now equal to a product of projective spaces, okay. Right. Okay. Yeah. The first one, and I have a hypersurface of degree d1 through dr, right? Then, if each of my ni's are at least 2, if each of my degrees are at least 2, okay, then x being smooth implies we have all the finite. And here, the smallest hypersurface I can have is a threefold, so I don't need to worry about these three guys popping up. However, we can do better. This is the first one. The next one says, okay, if I'm in Pn cross Pm, and n is strictly greater than m, and Bn is allowed to be 1, Pm is not, okay, then the same. Smooth implies finite. And sorry, this is the other way around. I also need n to be at least 2. Okay. So it says P1 cross Pm. Now this kind of gets a bit strange. So here, if m is odd, then I need d1 can still be 1, d2 has to be at least 3, and m is even, and then it's the same as 1 is 1, 2 is 2. Okay. And given the, I'll show you kind of like how we structure the proof in a second, right? But given how we structure it, it's very algorithmic and formulaic. Right? For these products here, you want bot vanishing. You're just doing a lot of Cognate formulas of your cotangent model. They will split up, so it's very computational. And so we've tested this on by now I think about 15,000 hypersurfaces, hypersurface types. So I know what the right things are. Okay, I know exactly the bounds of how to improve this, how to let some of these be 1 and let some of these be 1. But the mechanics of proving it, I mean, even proving this is a bit of a nightmare. It's a nightmare in like numbers. If you imagine, like, you see my bot vanishing here, I have 3 variables. I have K, I have P, and I have D. Right? So I have this kind of like 3-dimensional lattice of these cohomologies. Right? But the direct Spencer method is about picking 2 lines inside this lattice, okay, showing that they're all 0. So just basically about, sometimes you find these lines and they work, they all vanish, but you need to show that they're always 0. In general, it's just a bit of a mess. But this is the best you can do as a theorem, and conjecturally, it will be in the paper. Yeah.
But can you explain what is the notation of the lower D1 up to here? Is this the 0?
This is the bi degree, or the multi-degree, right?
Oh, okay.
Right, pick our group of y is just z plus z, like r copies of z, and my d just happens like here. Okay, so let's a little bit of time left. Yeah. 16 minutes with questions. 15 minutes with questions. Yeah, so that gives me 5 minutes to kind of show you a bit like what's under the hood. Leave that one up there. Here's this one. And talk about some exceptional cases. And like for me, the kind of most fun part of this project was working through the exceptional cases. Like there are some cases where our method doesn't work. Okay? And exploring why is yeah, it's an exercise in doing lots of jobs. So yeah, proof idea, right? And essentially, it just revolves around this idea of Kodaira-Spencer. So we call it the Kodaira-Spencer descending method, basically. And it works as follows: like, it's essentially you take Poincare residue of P form. Okay. And now this was something for me, this was completely new, right? But people doing kind of logarithmic geometry and logarithmic stacks, this is completely banal, right? And you just kind of lift it. So banal that like I can't find references for it, right? So we have to prove it in an appendix. Like, but basically, right? So you take I take my one forms, right, on y, okay? And y is so what's my setup first? I should be explicit. So x is sat inside y, and it's both are smooth. X is a Cartier divisor. Okay, and secretly what's going on, right, to make this kind of non-standard is that x and y are both smooth DM standards. Okay, that's kind of what the new part of it is. For the schemes, this is Katsana. And we have P forms, or let's take one forms on y, right? And I can take the tau local coordinates, and they are given like they're by y1 up to yn. Okay, and I assume that the tau locally x is given by the vanishing locus of yb. Right, I can do this because everything's smooth. Find some tau neighborhood where I can look at it. Okay, and these are sat inside so-called logarithmic differentials. Right? And here I just take a new basis of d log y1, right? dx1 mod xi, mod over xi, dx2, etc. Okay. So these are sat inside here, and a general element now of a P form, right? So I can take exterior powers, alternating powers of this, and I get my P forms on Y. That's inside my P forms with poles along X, right? And now, those of you, so maybe most of you have probably at some point had to teach some complex analysis, right? So if I have a rational one form, okay, just in one complex variable, and I integrate around it, right? This gives me my residue, okay? And Tate showed us how to do this over any field, and in fact, it generalizes to P form, and it generalizes over and it also generalizes to like P, same deal. I integrate around it, and I get a P minus one form on X. Okay. Again, this map is literally, it's called the residue. So great, this is now one short exact sequence, right, which I can put into this algebraic geometry method of just taking homology and checking things. And I'll need one more. Just kind of say it out of interest. And basically give the kicker. So I might switch to blue as well because black's been faded. We also have a so-called restriction map. Okay, this one I won't explain for interest in time. Restriction sequence. Y log y minus y. Y X. Okay. Doesn't matter really what these are. The point is, right, I can twist these by line bar, and they remain exact, and I can take homology, right? And then I can start comparing, and I know some are 0, then I know others are 0, and this gives you kind of a mechanism to work with these things. And we kind of prove this lemma, which says that, okay, if for every k greater than or equal to 0 and epsilon equal to 1 and 2, I have the following bot vanishing, which is hk of y. I take, what is it now? It's n minus k minus epsilon. Twisted by, I have minus the canonical of y minus k plus 1 x. Okay, this looks like an absolute nightmare. Right? If I have these guys all vanishing, then h naught of t of x is equal to 0. This lemma is really the powerhouse. This is what we prove, like, actually holds for any smooth setup. Okay. But this is great now. Now I have not all of this vanishing to check because, in various pieces it doesn't vanish where it doesn't have to vanish. I have these two kind of, for each epsilon 1 and 2, I have this whole line. The step in k is bigger than the dimension, right? It's 0. You have some descending induction which combines these two guys and kills off exactly the ones you want. So you've turned vanishing of the tangent bund of global vector fields on X, right, into vanishing of homology of P forms on Y, okay, with some poles around. So it's not poles, but zeros around. Okay, this is the method. And like this, it actually, we have some kind of like machine basically that we have a machine which eats the toric variety. You give it a polytope, it will tell you whether it satisfies the right kind of function. Polytope gives you a toric varieties plus a hypersurface. Eats it. These things are given by lattice point counts for toric varieties and okay. So that's roughly that. I mean, that's how we prove it. Right? Spare you the gory details. What about the exceptional cases? I guess I have 5 minutes, so I'll tell you about them. I'll tell you about two things which I like. Okay, so ways it can fail. The first way it can fail, right? So
Can I just ask?
Yeah.
What do you say automorphism group?
This is the Lie algebra of the automorphism group. Right. So if I take x to be of degree 2, 2, 2, right? Sometimes I wish I'd studied like arithmetic geometry and K3 surfaces. I think they're so pretty, right? But here this is 1 plus 1, 1 plus 1, 1 plus 1. Okay, so this essentially means it's a K3 surface, right? And these are called Wheeler type. Okay, they're well studied. And I have 3 different projections here, right? I can project to these two, I can project to these two, I can project to these two, right? And using these projections and swapping around the coordinates under each of them and then pulling back up, okay, I get an infinite group of automorphisms, but it's discrete. Copy its free product of Z2 and Z2. Okay. Very nice. Oh, right. But this is discrete but infinite, and indeed, if you apply this mechanism, you can show it satisfies all the required vanishing. But this restriction thing going between the stabilizing and the automorphism doesn't work. This is infinitely discrete. Okay, since I only have time for one more example, get on with it. Another one which doesn't fall in our purview is if I take degree 1, 2 inside P1 cross Pn. Okay, with M, but take M equals 3. Okay, so P1, P3, but in general, fails for M of. Okay. But what is this, right? So now you can really do some geometry, but if it's degree 1, 2, then this is defined by an equation which looks like, so coordinates on P1 are x, coordinates on P3 are y. It looks like x naught times some quadric, even naught in y, plus x1. So this is just a pencil quadric. And indeed, X is isomorphic. It's just given by the blow up along the intersection of these two quadrants of Pn. Right? Which, when M is 3, this is an elliptic curve. Right? Again, you can do these numerics, whatever. You can intersect these guys. It gives you an elliptic curve. And the Jacobian of this elliptic curve, the H, so H1 of OC, OZ, sorry, pops up in this very annoying place inside y, omega 1. Okay. It doesn't die. Okay. So it's like, but this is kind of a very famous classical construction. This is actually Mars-Reid did this in his thesis. Right, showing the intermediate Jacobian of this guy kind of pops up with the elliptic curve over the base of what it blows up. And it's really like, see, so the failing of these homology groups tends to give some really nice geometry. And there's another kind of class of examples where if I let this be 1 and this be any number, then I end up with some projectivized bundle as my hypersurface, and then conditions on splitting and non-splitting and stuff. Like the geometry is just very rich. But I'll stop there. Thank you.
Depending on the case, from degree and from degree and come in, can you bound the automorphism?
I can't. People can. The C for over the.
I recently proved that you can bound.
Yeah, exactly. Over the complex numbers, S can bound.
Yeah.
And I mean, I just never looked over that specific part of the proof to see if it generalizes to these numbers. But actually, I mean, it relies again on an excisable vacuum, which is true over any field. So I imagine it's the same. But I've never proved it up. I don't want to tell you something. But I think probably yes. Yeah, you can bound it, and it will be in terms of degree and weights. The other interesting thing which Etta does when he's looking at these things is kind of prove that if you have, like, the next question, right? Okay, we know they're finite. Like, when are they trivial? Are they generically trivial, right? And the answer again is no in general, but they have some generic guy which you can find and you can compute. And because so people seem to be interested in computing these things at the moment, like it would be interesting to now introduce positive characteristic cases, so you could really, I don't know, the behavior will be different, and I don't know, it will be interesting to see what happens.
So, how representative is this example of when things go wrong?
Good one.
Yes.
In the sense of being infinite but not infinite but not finite.
Is this as bad as possible?
This is as bad as it gets. Yeah. If I had time to, like, when the dimensions of the K3 was given. Yeah. I actually don't know. It's very
So it strikes me that this happens to be a graph of groups in the. There's a thing called a graph of groups. We're taking a special example where the things in product are finite. Is that?
The geometric reason behind stuff
Yes.
has nothing to do with embedding the calculated surfaces and the canonical line bundles figure. And any automorphism group has to preserve the canonical line bundle. If it wasn't trivial, you can probably use it to get either the canonical line bundle or the anti-canonical line bundle to get your morphism somewhere else. And then deduce at least something about the group of trivial. You can only use it to send it to a point. It has no automorphism group, so you're not going to get anything, and that's why these polygens appear.
So we wouldn't in general expect to see just frequent lots of finite groups.
I mean, strange things happen. I mean, like at this point, right? So, like the way that you study K3 surfaces is you look at their Picard groups. I mean, they are in general very interesting lattices with very interesting non-degenerate pairings on them, given by geometry. And so, if like the answer to your question, I think is if they come up, if they also arise somehow, they have to fit in and mesh with the lattice theory. Basically, you need automorphisms of these lattices. And yeah, I don't know how to answer your question, but I suspect that lies somewhere in this lattice theoretic approach to it. Yeah. Oh.
Any more?
I think first. So, when you say you have some conditions that are required to give you final automorphism, and then there are all the situations where the conditions are not satisfied.
Yeah, yeah.
So, for all of those, can you always prove the automorphism?
So
How sharp are these conditions?
yeah, so the conditions are like the conditions here are not shown at all. Each individual case needs to be looked at. So the nice thing about this method is that it proves it. It doesn't prove it for a general element of your linear system. It proves it for smooth.
No,
So,
I know that.
Yeah,
That's
but
not what I mean by conditions.
No, but what?
The degrees and the weights.
Oh, they're sharp. Like this. Well, they're sharp in terms of like this method fails if these aren't met.
Right.
So, but the automorphism group, yeah. So it gets interesting. Like for example, I rubbed them out. That's a shame. In these ones here, these automorphism groups are finite always. Okay.
Regardless.
So this is like somehow this. Yeah, we can't prove it with our method, and it means we have to ignore characteristic 2. But this is always true for these blobs. However, if I swap these two round, then I end up, instead of a blow up, I end up with a projectivized bundle. And then it's genuinely interesting. You have a linear system, you have an open dent where the automorphism groups are finite when the bundle that you cook up is non-split, but you have elements on the boundary where you have it, which are toric actually, like which have non-trivial, which have a torus acting on them. Because the bundle splits and you have some toric automorphism of the bundle. So like there, that's what I mean. Like geometry is rich. It's interesting. It's difficult. And they're still smooth.
But for instance, in the second theorem, the one in black.
Yeah, this one here.
Yeah.
I have.
If you drop the degree to 1,
Yeah, then it's delicate.
it's delicate, but maybe it's finite and probably just 1.
Yeah.
Okay. And I guess this, like that condition on the top, this degree larger at 2 months.
Yeah, that's sharp.
Does that cover all general type?
Yeah.
Yeah. Does it cover all fun of qualities? Like
Covers all interesting methods.
and I share.
And that's sharp.
The degrees are smaller than your.
I don't know. I'll give you the archetypal count example. You tell me if this is. If I take the degree 4 thing inside 1, 1, 2, 2.
Oh, sorry. Yeah,
that's beautiful. But like, if this is interesting for you, then unfortunately this doesn't work, and this actually has all infinite. Yeah.